Welcome back. And before continue, I will also like to mention that I have uploaded. Oh, sorry. Don't want to leave. That I have added links to downloading Octave, which we will need for the next week practical exercise. So you can install it. And there is also even online version, which does not need installing and can be operated from Chrome or any other browser program. So please install by the next week this program, and we will use it over the entire course for all our practical exercises, for all course project calculations, and so on. Also, if you have MATLAB from maybe your school, then it's okay also to use MATLAB. They are the same, basically. Well, MATLAB is better, actually, of course, because it's a paid program and has a lot more toolboxes, better graphics, and so on. But Octave is sufficient for our tasks, and we will have all the files necessary available for you as well. So yes, let us then go to the structure of the communication systems. I have changed a little. I have taken a little bit different picture, which has more information. Yes, about what we'll discuss here. And now we will basically go through each block of this structure to see what it does. Yes, we only get this into small details today. We don't really delve into, but over the duration of the course, we will take a lot of time talking about source coding, channel coding, modulation, yes, also line and noise, and according to demodulation, decoding and decoding, yes. And maybe we'll skip, not so really skip, we'll not mention a lot of time to scrambling and interleaving. This block, by the way, is missing in this diagram. And well, I'll tell you where it is when we get into that place. But okay, let us start. As I mentioned, there is a source and there is a destination, and the task of communication system is to send the message with information from source to destination just precisely as it is only possible. Yes, with the least possible number of errors. Yes, ideally this should be the very same message, but in reality, of course, as you understand, some errors may happen. Partially these errors can be corrected, but well, depending on what type of data it is exactly, these errors may be critical or maybe not really. If it is, for example, banking account operation, then of course every error there is a critical error and it cannot happen. Yes, so there needs to be good protection from errors and so on. But anyway, let us start. So as I told, source and destination produce a message which is not really suitable for sending in communication systems. This can be picture, this can be sound, this can be anything we can work with. Basically, this can be even some text on paper, which can be scanned and sent, such as fax system is working, and so on. So the source and destination, as I mentioned previously, are not part of the system. They are just a person or other devices of any type who is working with this information. Yes, so store, process, and do anything like this. And the first thing we need to do is to actually convert this information from the source format to format which is suitable for working in our communication system. So basically this is the transmitter, and we need electrical digital signal for this to work. For that we use formatting device. Accordingly, here we perform the reverse conversion, yes, inverse conversion, and convert digital signal into some format which is suitable for the receiving part. Well, if it's person, for example, and it uses he uses a monitor, then we need to convert these binary symbols into some picture on the screen. Yes, and here vice versa, we convert picture into binary digits, and then furthermore the system is working with these binary symbols. So it will become more clear during the course if you didn't really understand it right now, but I hope that today's examples will show you how it works and it will become much more clear to you. So this is the preparation of the message, yes, formatting device. And this includes actually all kind of different sensors, yes, such as microphones, light sensors, and so on, that convert physical processes such as sound, light, temperature, pressure, anything else, yes, into an electrical signal. So basically, this physical process is converted into electrical signal with which our system can further work. We don't really discuss these sensors in this course because these sensors can be very different, and well, there are definitely according courses about the sensors themselves, definitely. And what is more important also is that actually sometimes this source can already provide binary information by itself. So, for example, the source is computer in some network, and it already generates information in the way that is suitable. In that case, formatting device can be used to make some kind of packets, frames, and so on to group information. Yes. So this is also another use of the formatting device. But in general, we need conversion from a physical process into electrical signal, and furthermore, from the electrical analog signal into electrical digital signal. And on the second end, at the receiving side, we usually convert digital signal into analog signal. So again, digital to analog, analog to digital conversion are covered by other courses. I think maybe even you already know this, but I'd like to remind you, if you have forgotten or didn't know yet, maybe how it's happening. So basically, analog to digital conversion is happening into two steps. First is time sampling, and second is level quantization. So imagine we have some continuous signal represented with blue line on this picture, yes, some analog signal, which we'd like to convert into digital signal. So the first step is to read specific points of this signal, specific samples. So this process is called sampling, yes, and this sampling is performed with some specific sampling time interval, which needs to be correctly selected if we'd like to reconstruct the signal later on. So basically, if we connect these points with some line, yes, it is possible to receive almost the same signal as it was before converting into samples, yes. However, if we choose these points not often enough, let us take another example. Here, let us say maybe here, here, also here, and here. Yes, so in that case, if we try to reconstruct this signal, it is impossible to receive original signal only because we didn't take enough of these samples. Yes, so this sampling time needs to be correct. Yes, so this is actually proven by Nyquist, Shannon, and this is called a sampling theorem condition. Sampling theorem. So you may look up it if you haven't already did this in other courses. So if you had, I apologize, but I'd like to just make sure that you understand what I'm talking right now about. Sampling theorem. So this sampling time can be the same, that it fixed, or it can be variable. Most often we are using fixed sampling time, yes, because with varying it's quite difficult to work. There are researches happening with variable sampling time, but this is still far from any commercial system, and so it's only theoretical interest currently, yes, but it's possible, most definitely, but it's more difficult. So it's easier to know that after certain amount of time you're expecting a new sample of data. Yes, currently the level of these samples is still the voltage, yes, and without any changes. So this signal is called discrete signal. This is not yet digital signal, this is just discrete signal, which exists only in specific time moments. Yes, its amplitude, however, wasn't changed in any way. Now, if we perform the similar operation to the amplitude, called quantization, then we obtain a digital signal. So digital signal, you can think of it as some kind of rounded off version of discrete signal. So here you can see in picture red a digital signal, in blue discrete signal. So digital signal can take only specific values, yes. So basically that is why it's called quantization, because very similar to quants in atoms, they can change only with some specific steps. And it's impossible, for example, for the digital signal to have value like this. And each level has a digital code assigned to it. Yes. So you can see here 3 binary symbols code to each level. So what happens if our actual signal value is somewhere between 2 levels is that we are rounding it to the closest level. So in this case, it was closer to here. In this case, it was closer to here. Yes, so very similar as we are rounding numbers. For example, 0.75 would be rounded to 1, and 0.3 would be rounded to 0. Yes, so this is the same. And now, after this operation, the signal exists at specific time intervals, and instead of voltage amplitude, we have digital code. And this can be represented as integer numbers, for example, very similar, like this is 0, this is 1, this is 2, this is 3, 4, 5, 6, and 7. Yes, and these numbers can be worked with. Alternatively, we can work with these binary symbols themselves. So this is our information after conversion. And in this format, it doesn't really matter what was that signal originally. All that matters is it 0 or 1? Yes. Here we have 3 bits per code word. So this gave us 2 power of 3, which is equal to 8 levels. Obviously, if we take more levels, yes, the picture would be more precise. The blue dots and red dots would match much better. And here is like, how to put it, dilemma, yes, how many levels you need. Because from one side, more levels gives better accuracy and signal is closer to original. On the other hand, however, this also gives you more and more data to process. Yes, so basically each additional bit doubles number of levels, but also makes your code word longer. You need more memory, you need processors working with larger amount of bits, and so on. So this needs to be chosen per how to put it, per application. Yes, in some cases you need, for example, 8 bits per level. In some cases you need 24. So this can be best shown for audio. Yes, there is a standard for telephone calls for digital communications that we use a sampling frequency, f sampling, which is 8,000 Hertz. Yes, so basically this way sampling time would be 1 divided by this sampling frequency, like 0.125 milliseconds. Yes. Wait a minute. Let's check. 1 divided by 8,000. Yes, milliseconds. Or accordingly more zeros and seconds. So this is the sampling time. Oh, sorry, sampling time for regular phone calls used in mobile telecommunications, in digital phone lines, yes, and so on. As for the number of levels, before that, wait a minute. Before that, I'd like to justify why was it exactly 8,000 according to this time sampling interval theorem. The thing is that our normal talking spectrum, yes, here we have frequency, is basically in range of 300 to 3,400 Hertz. So in this range, our voice is, when we talk normally, we don't sing or don't cry or anything like that. Yes, we have some, for different sounds, phonemes, we have different formantas, let us say so, yes. And this is the spectrum of some specific sound, yes. For example, A. This is not really A, but let us assume that this is A. B would give a different spectrum and so on, but all of them are in range from 300 to 3,400, yes. And according to this theorem, we need to choose sampling frequency of at least not less than double f high. So in our particular case, f high is this one, yes. So this means that we would need to choose actually 6,800 Hertz sampling frequency. Well, however, there is also one more thing that we need to take into consideration, is that actually in real life, the spectrum doesn't really end here. Yes, something also is there. This is just insignificant information which can be skipped, but it still can interfere with our signal and degrade quality. So for that reason, we need to use a filter. And filters, sadly, cannot be implemented like this cutoff frequency. This is what we would like to have. However, in real life, we have this transient process, yes, in frequency domain. So somewhere here around 4,000 Hertz, the attenuation is good enough to consider that from this point there is no signal anymore left. Yes, so that is why, because of this filter, we took 4,000 and doubled it to get these 8,000 Hertz. So this is for phone calls. As for the number of levels, yes, as for the number of levels, we have 8 bits per code word, which gives us, to a degree of 8, 256 levels. Yes, so this way we have 256 levels, which is enough for simple talk over the phone. Yes, and in general, this gives data rate of 8,000 Hertz multiplied with 8 bits of the standard telecommunications phone channel 64,000 bits per second. This way it's calculated. Because hertz is at the same time 1 divided by the second, yes. Bit divided by the second, the dimension is correct, and this is the multiplication. So this is for normal talking. For audio, for music and multimedia, there are different things, yes. For multimedia, we usually use much higher sampling frequency, yes, such as 44 kilohertz or 48 kilohertz. There are two standards for the CD quality, yes. And basically this is again the same. We have spectrum. Our ears can hear frequencies of up to, usually on average, of up to 20,000 hertz, yes. That is where ultrasound starts. And we again use some filter which cannot really suppress frequency component starting with this, and has some of these transient line, yes. So this basically gives us 24 or 22 kilohertz, and that's how these numbers are obtained. As for the number of bits, maybe you have heard or seen somewhere, or if you open any MP3 file, you will see there, for example, 24 bits per sample. That means that actually there is a total amount of 2 at the degree of 24 of these levels for music MP3 files. Yes, you can easily calculate. I can perhaps show you octave. And 2 at the degree of 24 is actually this large number, yes, 16 million, and so on and so on. So for math long, maybe this way it will show us, yes, what exactly is this number. So these match levels for music, these match levels for regular speech. Yes, as you can see, the number of these levels can be very different. Yes, as the same goes for the picture itself we're seeing on the screen. So we have 16-bit pictures, colors. Yes, we have 32-bit colors, and basically that's more than enough for our eye. Yes, because if we take even more bits per pixel, our eye wouldn't be really able to distinguish much. Well, at least maybe most of the people. Yes, I'd say maybe some people would really be able to tell that where is 32 bits or where is 64 bits. But for the most people, it wouldn't be very indistinguishable. Yes, so this depends basically on the application. How many levels do we need? Okay, so this goes for formatting device. And after this formatting device, here we have sequence of binary zeros and ones with which we can work further. So everything that happens here is performed by microprocessor or microcontroller of some sort. Yes. Up to here, we had analog to digital converter, some sensors, yes, and well, here was the source. So the good thing is that further everything is performed on the same chip, basically, at least in modern communications, modern devices such as your mobile phones. That's how it's happening. Yes, this is called digital signal processing, DSP for short. Yes, and well, that is entirely different story and entirely other big course, which maybe you will have, maybe you will not. Some things I will definitely show you during this course, which are most important, but you need to understand that there is a lot more left undiscussed after this course, so you will have somewhere to grow further. So the next block here is source coding. So this is basically some information represented by binary symbols. Yes, message coded in binary form. And it turns out that not all of these symbols are equally important. Well, that is really easy to show. Let us take any word, for example, communication. Yes, communication. Now I will skip some letters. Communication. And it's still somewhat, well, although much harder, but somewhat distinguishable, yes, that it was indeed communication. Now, however, if I skip these letters, like what I have written, and will use only these letters, like O, U, I, A, I, O, it's much harder to understand that this was actual communication if I wouldn't tell you, yes, than in this case. Well, that is happening basically because not all symbols have equal amount of information. Some symbols have more information than others, and some are not so significant. And this way we can compress our message to make it transmit faster. Yes, and that is basically what source coding does. We will have detailed discussion of how source coding works in your course project. We will also be tasked with making such a code. Yes, but the idea is very simple, that we extract some non-essential information. There are two types of coding, source coding: non-destructive compression and destructive compression. So for non-destructive compression, the original and restored message are exactly the same. You cannot lose anything, yes, in that. So this is basically used for archives such as zip, rar in our computers when it's unacceptable to change any bit. Yes, so uncompressed message must be exactly the same as original. And there is also destructive compression when some slight changes are allowed. This is basically used for pictures, JPEG, for videos, audio, MP3, MPEG. And most often it allows to achieve much higher compression, yes, because for JPEG, for example, picture, we make some neighbor pixels the same color, although originally they had a slightly different color. We make it more rough and assign the same color, which is, for example, average color between two pixels. And our eye may not even notice this difference. Yes, this may be not important. And well, of course, the higher the compression ratio, the more information is lost, and sooner or later you start noticing these things. You can hear worse quality, for example, or see picture with some artifacts, and so on and so on. This so basically depends on compression ratio, how much we compress information. So for non-destructive compression, as I said, no information loss is allowed. So after the coding, so at this point, yes, here, this message and this message must be exactly the same up to the last symbol 1 or 0. Yes, for destructive compression there are allowed some differences, yes, which are for this receiver not really observable or maybe tolerable, let us say. So maybe you can see that the picture is not so good as it could be, but it's fine, and well, it's good enough for you to do some work, for example. Yes, because well, for example, communications. Yes, if we talk about mobile phones, there is, as I said, one data rate, 64 kilobits per second. And now the quality of the voice, the understandability of the speech is good. Yes, basically we can understand what is being said to us and who is talking to us also. However, there are some professional systems used by police, by military, and so on, which has much lower this value. They use special coding, yes, for example, 8 kilobits per second. And in that particular case, it's no longer possible who is talking to you. You still understand what is being said to you, but the voice is very unnatural. And well, in that field, it's not really important, yes, because much more important is to actually send the correct information, not make some understanding who is talking to you and so on and so on. So yes, that is an example of how this destructive compression can work, yes, to lose some insignificant for specific task information. So as for non-destructive compression, we can also imagine some how to name it, I don't even know. You know, this thing you use to wash dishes and so on. I just forgot how it's called in English. Yes, and you can imagine it as our message. Yes, and it's containing some water. Yes, so basically, what happens when we use compression is that you, well, actually compress it with your force. Yes, the water is exiting this thing. For example, we put that water in some bowl, and for non-destructive compression, you then transmit this dry sponge. Yes, I think I remember. So it's going to be called SpongeBob. Yes. So you transmit this dry sponge somewhere, relocate, and if we are talking about non-destructive compression, you need to immerse this sponge into exactly the same bowl with exactly same water that there was before to get the original wet sponge. Yes. Now, if we are talking about destructive compression, then you can utilize this water and use a new different water, yes, a little bit, but the effect will be still the same. This will be just a wet sponge, yes. So this is basically the difference, that we need to keep all the details for non-destructive compression, and for destructive compression some details are not important and minor information loss is tolerable. This, however, gives us much better compression ratio. So as if, for example, for non-destructive compression, we can achieve like compression of like 25% maybe, or even less, then for destructive compression, we can actually compress 10 times or even more, yes? So much higher compression. But as I said, not each data can tolerate minor information loss. So it needs to be double checked. Yes, as for speech compression in communications like mobile phones and military radio, there is specific algorithm used called LPC coding, linear prediction coding. This is in fact very interesting thing. Maybe you just don't realize it, but what you hear in your mobile phone when you talk with somebody is actually artificial speech. It's not recorded speech and sent. This compression works like you have some, as I've said, showed you before, formantas, yes, of some specific sound. Then the algorithm determines what frequency is for each formanta. Frequency 1, frequency 2, frequency 3, amplitude, amplitude 1, amplitude 2, and amplitude 3. Then makes regression model, transmits this regression model, and on the other hand, on the other side, your phone reconstructs this spectrum from this regression model, and you can hear the same voice. You can even understand who is talking to you, what is being said to you, as if the person was near you. But this is actually synthesized speech. Yes, a very similar way, like you know, Google talks to us and so on. Well, that's and compression ratio in this case is also around 10 times. This is working only for speech. This is very specific coding type. So we have compressed our message. Now it's smaller and can be transmitted faster. Yes, however, this comes also at some cost. And after we compressed message, we removed this redundancy. So in example with our sponge, yes, when we compressed that sponge, this water was redundancy. This was what we didn't transmit. However, this redundancy also helps to receive information accurately. So meaning that after we have compressed our message, any error will be much more devastating. So indeed, it's quite easy to show that this redundancy is helpful. Yes. So for example, assume that you are transmitting something, and at some particular case, you send letter A many times. So your message is just sending letters A. At some step, an error happened. Yes, and you have received, instead of A, C, for example. Now, knowing the fact that you have received only A letters, you can safely assume that instead of C letter, it was meant to be A letter. Yes. Now, what happens if all your transmission is just a single letter A, and you have received letter C? Then you don't really know, was it meant to be A or was it meant to be C? You are not so certain anymore, like it was here. Yes, so, and the repetition is actually the form of redundancy. Yes, because basically the new information was only here. Yes, and the rest is already known information. This is excess information. Yes, not needed for communication system for us, but very useful to increase reliability, that you actually receive the correct message. So this is actually what's happening in life for us. Yes, when there is some important information you want other person to know, yes, you are reminding that person about it. Yes, this is repetition, this is redundancy. Somebody may get annoyed by that, you know, but still this is better to be sure that the person didn't forget something, and so on and so on. Yes, and after the compression, this reliability is worse. Yes, so in order to compensate for that effect, we are adding another code, which is designed to actually add more redundancy to our code, but in such a way that this will allow to correct errors. So I will describe this with example now. Yes, and we'll also work a lot on these codes during our course project. So we'll study two types of the codes, group and cyclic codes. And some of you will have cyclic, some of you will have group codes. Accordingly, in exam, you will have different type of codes. So each of you will have the chance to know both of those codes. Yes. So the redundancy being added is calculated, meaning that we just don't put any water into our sponge, but we put a very specific type of water with some maybe minerals or other adding, if we continue that example. Yes, but when it will come to example, it will become much more clear. So basically, we add specific redundancy, not just any redundancy, not just anything to our message, but very specific symbols in order to allow this message to be checked or corrected for errors. So we can have different types of codes which can only tell you if there is error or not, codes that then correct single errors, separate errors, yes, and code that can correct multiple errors, yes. So very simple example. Consider that we have communication system. So here we have transmitter, which is sending information 0, 1, 0, 1, 0, 1 in the channel, and we have receiver. What we'd like to know here is how can we make this message more securely received to avoid errors. So first, let me tell you that the errors happen by changing symbols. So for example, combination 0, 0, 1, 0, 1, 0 has an error in the first position. Yes, because we sent 1 and we received 0. Now we'd like to add some mechanism which will allow us to tell that there is actually an error. For that, we need to add extra information here. So basically, we send more data than necessary, which is called redundancy. Yes. So in this particular case, we add either 1 or 0, only one symbol, in such a way that the total number of symbols 1 is even number. Yes, so we have here 1, 2, 3 symbols 1. Therefore, we need to add 1, and there is total 4, which is even symbols in this message. Now consider that we have sent this information and the error occurred in this first symbol. So the law of the code is that any correct combination has even number of symbols 1. Yes. Now, if we check the number of ones here, we can obviously state that this is odd number, not even, and therefore that is an error. That has been detected, and indeed there was an error in symbol 1. This is the most simple code, which is called parity check code. It adds only one symbol and is capable of finding any odd number of errors. So if we had 3 errors, that would also work. If we had 5 errors, that would also work. However, if we have 2 errors, that unfortunately will not work. Yes, this code will not be able to tell when happens 2 errors, when happens 4 errors, and so on. Yes, because the number of ones is even, which is assumed to be correct. Yes. This is the very simple idea how these codes work. Now, if we add more data here, this can actually enable us not only tell if there is error, but also to find out where exactly that error has happened. And we'll talk about this during this course, how to make such codes, how do they work, and we'll see with examples. But for now, let us continue. We'll return to this topic about the errors right now in discussion of the interleaver, which is a non-essential component, so it's not pictured here, but well, I will add it here like interleaver. This component is not mandatory. The system can work without it, but it can help with channel coding. And here accordingly will be here accordingly will be the interleaver, the block that performs opposite operation. So what it really is, that's interesting thing, interesting component that actually changes the order of the symbols. So consider that you are sending symbols A1, A2, A3, A4, A5, and so on. And interleaver changes how these symbols are following each other. So instead of this sequence, we'll get, for example, A1, then we get A5, A9, A13, then somewhere here A2, A6, and so on. So the order is different. There is a natural question, why do we need to do that? And the answer is very simple. This way we try to separate errors which may happen simultaneously. So consider, for example, that during the transmission we have errors in these three symbols. Yes, if we do not do anything, then these symbols will be inside the same code word. Yes, let us say this is the code word, and the code needs to find and correct three errors in this case, which is very difficult code. Yes. Now, let us assume that we did interleaving, and instead of three symbols A2, A3, and A4, the errors have happened in symbol A5, A9, and A13. This way, these three errors won't be concentrated into the single code word. If we are lucky, even it's possible that in each code word we will have only one error, which can be corrected with the most simple Hamming codes, which we'll study in this course. So these multiple errors is called an error packet. Yes. And accordingly, it requires the codes capable of correcting packets, error packets. Yes. We can see it here that these are the simplest codes and these are the most difficult and advanced codes, which also require more computing capacity as well. Yes. And these are somewhere in the middle. So what we'd like to do is to convert these error packets into independent error and stick to simpler codes. And interleaver allows us to do that. So how does it work? Let us say, for example, that we are using Hamming code, cyclic code, yes, which is capable of correcting one error per 7 symbols. So we have here data information block of 4 symbols, and we have controlling symbols. Very similar way as we were adding in parity checking code, that 1 or 0 at the end, depending on odd or even numbers. So in this case, we add this control number, and this control number needs to be calculated from this data. So this data will give this control. Other data will give other control symbols. And basically the idea is very simple. Now we calculate, we send this information, we receive data, calculate control once again, and compare received control with calculated control. If control matches, then there are no errors. If there is a difference in control, yes, then there can be 7 different combinations of this difference. So the difference of control can be this, like this one, this, and this. Yes, so 7 different, let us say, so changes between these controls. Yes, and it turns out that each of them represents, how to put it, that we also have 7 symbols. Yes, so for the error in the first position, we'll have, for example, this difference of control. So if the controls differ by this number, then we know for certain that the error is here. If the difference in control is this, then we will know for certain that the error will be here, and so on. So this is a brief idea how these codes work. These control symbols are calculated as the reminder of the division. Reminder of the division. So we divide this data with some special generating polynomial and get this as a reminder from that division. Accordingly, we merge this, send together Then at the receiver side, we again separate these data, again calculate division, again find remainder, and compare this new remainder, which we calculated, with this reference reminder, yes, which has been sent alongside with our message. And this way we find where the error has happened. So this is the brief idea. Now imagine that we have 7 such code words. Yes, here is the code word 1, code word 2, and you can see that for different data we have different controls. So here we had data 1010 and control this, and here we have data 1101 and control will be this. Again, other data, other control. These are in fact actual Hamming code words. So when you will learn enough of the Hamming codes, you will be able to check this example and confirm that it's actually correct code words. So we have 7 code words. We have so basically this code, as you can see, adds a lot of information, extra information. Yes, we have 4 data information and 3 control symbols, which we need to send per each 4 information symbols. This basically gives that instead of sending 4 symbols, you have to send 7. Yes, which is quite a lot in percentage improvement. Not really improvement, but increase in volume of data. Well, this comes at the cost of capability of checking and correcting errors. Yes. Okay, so how does Interleaver help us in this situation? Now, let us assume that we have 2 error packets happening when we transmit this data, here and here. Yes. Now, if we don't do anything and use this as it is, so here is our first code word, here is our second code word, here is our third code word, which were affected by errors. Yes. No, that last one wasn't belonging. Yes, it's like here. So Hamming cyclic code can correct only 1 error. So as we can see, in no situation, yes, here we have 2 errors, here we have 3 errors, here we have 3 errors. In none situation, this code would be able to correct it, because what happens when you have 2 errors is that actually Hamming code thinks that it is 1 error somewhere else, not in these 2 symbols, and tries to correct it. For example, it would assume that the error is here, and instead of this 0 will make 1, which is also an error. Yes, so correction of 2 errors leads to adding a third layer, add third error. So it does correction incorrectly. Yes, and we need to avoid that happening by all costs. Yes, let us say so. So now we have not 2 errors, but 3 errors here. The same happens here. Now we'll have 4 errors, and the same happens for here. Also, in the case of 3 errors, it is possible that for some specific combination of errors, not all 3 errors, but very specific combination of 3 errors, no effect. Yes, the code will think that everything is okay and will tell that there are no errors. Yes, this is also a possibility. So it will either add 1 more error or will not notice that anything is wrong. So as we can see, with Hamming code, we cannot really do anything with these errors, only make it worse. Yes. So let us use Interleaver to see if it will help us. So Interleaver works very simple way. As I have said, we need to mix data, change order, yes, but also keep in mind that you will need to return to original sequence somewhere later, yes, because the interleaver in this scheme here needs to put the symbols into correct order again. So you cannot just randomly change positions of symbols and then forget about it and hope that it will be okay. No, you need to understand that eventually here you will need to put symbols again into their correct positions as they were before here. So we need to have reversible interleaving. And it actually is very simple to achieve. Imagine a matrix which we fill in by writing data in rows. Yes, so here, here, and we read this matrix by columns. So basically, wait a minute, I think it's vice versa. Yes, so our first code word was like this, 1010101. Yes, this is actually vice versa. So we write data in columns. Yes, here is the first combination. And read data in rows. We didn't add any new data. We just reorganized this data. And that's it. Yes, change the order. So basically, after this interleaving, our data will look like this. Yes. So all ones, zero, well, I will write it. Yes, 7 1 symbols. Then 0 1 1 1 1 2 zeros. Then 0 1 0 and so on and so on. Yes, so we read this in rows and write in columns. And now we assume that the error packets have happened in the same positions. Yes, what that would be just comparison. Yes, so as you can see, these are no longer the same code words. So the question is where these errors will be after we reverse the effect of interleaver. So let us just do that. And this effect can be reversed very simple way. If we have written data in this direction and read data in this direction, then we need to do the same thing, opposite, yes, at the receiver side to reverse the effect of interleaving. And we do just that, yes. So we write data. Well, since our matrix in this particular case is 7 by 7, it's exactly the same operation. Yes, we write data in columns, read data in rows, and we can see that here is our first code word, here is our second code word, third code word, and so on. And only one of these code words has 2 errors. Other code words, this will be corrected, this will be corrected, this will be corrected, 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 and this one cannot be corrected. Yes, so it's better, although not perfect, but better. What we can do to improve this situation is actually change the number of the columns and rows in this matrix. Yes, and maybe we'll be able to actually make it better. So this shows that this interleaving actually can help spread the packet error into separate independent errors and use simpler code, because otherwise here we would need much more stronger codes, which are called Reed Solomon codes. Reed Solomon, which are capable of correcting entire bytes. Yes, so Reed Solomon codes work not with binary data, but with bytes. So for example, instead of this symbol, we could have from 00 to FF in hexadecimal form, yes, any value. And in 1 byte, as you can imagine, which can be from 00 to FF, consisting of only ones, total a lot of different, let us 255 possible error combinations. Yes, so our errors could have happened for example, here and here, or here and here and here, and so on and so on. And Reed-Solomon considers any of these possible error combinations as just one error. Yes, so here we have 8 symbols. Yes, just one error. 8 symbols, just one error, and so on. But Reed-Solomon code is much more difficult to learn and understand than Hamming cyclic code. Hamming cyclic code is one of the simplest codes, which was almost sufficient in this scenario, as you can see. Yes, the only code word that couldn't be repaired was this one. So Interleaver does really help a lot. Next block also is not really mandatory, it's optional, is Scrambling block. Yes, scrambling and accordingly descrambling. Now here is the timing problem of communication system. As you can see here is the clock generator, which controls all these operations such as formatting, source coding, channel coding, scrambling, modulating, and so on. And receiver also has his clock generator. However, in order for system to work correctly, these two clock generators need to be synchronized. Yes, they need to send clock impulses, well, basically almost at the same time. This is not easy task to achieve, yes, because generators are different. Well, they may be of the same model and so on, but you should know that even if you, for example, purchase a computer with some processor or some graphical card, even these processors, although exactly the same, yes, for example, I don't know, let us say i3 10300 CPU, for example, yes, multiple such processors will have different slightly different frequencies, yes, slightly different other parameters, so they are not exactly the same. Yes, so there is a slight difference in clock as well, and we need to synchronize this. This is very similar as to watches which we have. You have some watches, maybe someone still uses them, but mostly we use today mobile phones to look at time. Yes, but still there is some watches, and you need to check the time from time on time, and accordingly adjust time of your watches to show correct time. This is called synchronizing process, and this is exactly the same process what needs to be done for between receiver and transmitter. And it turns out that this adjusting, yes, can happen only when our data is like this 1 0 1 0 1 0 1 0. Yes, because this way we can see clearly our interval. Yes, and if we see, for example, that we have some time shift, yes, you can see that we have some shift here. This can be corrected by accordingly delaying one of these signals. Now, this, however, will not be possible if your data is like this 1 1 1 1 1 1 1. Yes, no changes in signal. So scrambling helps with that problem. Yes, so this is the bad case when you have a lot of ones. No, well, this is not quite a lot. Yes, this is just an example to show you that we have 5 and we say that it's a lot. Actually, a lot is like when we have 20, 30, yes, maybe 10 for some systems, but 5, it's maybe even tolerable. Yes, or a lot of zeros without changes. Ideally, we would like to have this signal which changes all the time. Yes, so scrambling does exactly that. Imagine that we have some data being sent that has long durations of ones or zeros, and we'd like to have more transients before ones and zeros. What we do here is we generate random sequence. This one is random, and add them together by using exclusive OR operation, XOR. This is also called addition by modulo 2, by the way. So A plus B modulo 2. So we add, for example, 1 plus 1, divide by 2, have 1, and a remainder is 0. So the answer is 0, yes? Very similar as to XOR. So XOR provides 0 if these components are the same, and 1 if they are opposite. So we can see that after adding this random sequence to these data, which originally had these zeros and ones, long sequences, these long sequences are gone after this process, yes? So we have successfully added more variability to our signal, which will help this synchronization problem. So this is not drawn here, but actually this clock frequency is controlled by a specific PLL algorithm, phase locked loop, which relies on data before the scrambling. Yes, so basically the idea is very simple. By using scrambling, we actually introduce this chaos into data. Yes, so we use this chaos by this PLL to adjust our clock in the receiver so that it would match the clock in the transmitter, and then we renew our data. We remove that chaos by, well, it's very simple, by again adding the very same sequence to this data. So if we add this random sequence again to this data, then we'll get this data. Yes, basically you can consider as if we subtract the very same sequence. Obviously, you need to generate the very same random sequence with this scrambler and with this scrambler. Yes, for that to work. But it's okay. You most probably already know that there are pseudo-random number generators, and one of these generator algorithms is M-sequence generator. So this is one used in scrambling. So these two blocks generate the very same sequence. This adds sequence, this subtracts this sequence, and our data is left again as original data. In the meantime, this clock generator is being adjusted, and this way we solve the problem of timing of synchronizing. So here is the reminder of exclusive OR function. Here is the what kind of random sequences can we use. We can use gold sequence. We can use Kasami sequence, which are both based on M-sequence generators. And we finally come to the most complex part of this system, which are interface with communication line. Basically, communication line is either some cable or optical cable or medium where our signal is transmitted, and only specific radio waves can be transmitted in that medium. Yes, so basically we need to now convert our signal from binary form, which is not suitable for transmitting in this communication line, into some format which will be good to transmit. Yes, so basically that's what modulator does. Well, we'll talk mostly about wireless communication in this course because it's very topical and I believe even harder than cable communications. Well, of course, cable communications also have their specifics, but making communications over the air is still more difficult task. So it's more challenging and more interesting to understand that. Yes. So let us assume that this communication line currently is of no difference for us. If it is cable or wireless communication, we still need some way to adjust our signal so that it would match the specifics of this communication line. And well, we'll return to this later, because currently I'm afraid this tells very little to you. What is amplitude frequency, phase frequency, and so on. I will tell you in a few minutes about that. But we are almost at the end. Okay, so the idea is that basically the spectrum of our digital signal, if we draw Fourier transform of our signal, yes, frequency, is concentrated in some low frequencies of up to some specific f maximum frequency, yes, which is not suitable for transmitting in radio waves, for example. For radio waves, we use much higher frequencies, such as gigahertz. For example, you may know that we use 2.4 gigahertz or 5 gigahertz for Wi-Fi communications, yes. And at the same time, the maximum frequency of the Wi-Fi channel is around 80, maybe 120 megahertz. Yes, so basically we have here 120 megahertz, and somewhere here we have 5 gigahertz. And we need to transfer this spectrum to these frequencies, because in these frequencies signal is not how to say is not sending well in the medium, yes, propagating. It's not propagating well. And for 5 gigahertz, it's much better. Yes, it requires smaller antennas, because basically the main criterion is the size of antennas. Yes, the size of antenna is related to wavelength, which is denoted by lambda, and the wavelength itself is calculated as light speed, yes, which is 3 by 8 meters per second divided by frequency, which is accordingly 1 divided by second. So seconds are removed, yes, and we are left with meters. So the higher is frequency, the smaller is this wavelength, and accordingly the smaller is antenna size. So let us see what will be antenna size if we use 5 gigahertz. Yes, so I will tell that C is 3 multiplied by 10 at the degree of 8. Yes, light speed in vacuum. I will tell that my frequency is 5 gigahertz, which is 9 zeros. Yes. Now I divide C with F and get a wavelength of this short, yes, in meters. So basically this is 6 centimeters wavelength, and antennas we use are usually fractional of this wavelength. For example, lambda divided by 2 or lambda divided by 4, and so on. So this gives us very small antennas of 3 centimeters. This needs to be for energy efficiency, yes, and that is why we try to use as high frequencies as possible. Well, at least that is one of the reasons, yes. And well, you can imagine if we use 120 megahertz frequency, let us calculate what length of antenna we would need in that case. Yes, C divided by F. That is around, well, if we use lambda divided by 2, that would be around 1.25 meters antenna, which is quite big to carry over in all places. Yes, so Yes, that is one of the reasons why we need to change the frequency. Another reason is that we are actually not alone to use the radio, yes, and there is a lot of radio stations. So here we have one radio station, here we have another radio station, another radio station, another radio station, another radio station, and so on. And you need to actually use the frequency range which has been provided for you. Yes, mostly these frequency ranges are licensed. You have to pay to use them. However, there are some unlicensed frequency range, such as Wi-Fi range, which doesn't require from you to pay anything to use. But again, all the people, all your neighbors can use the same range, and you need to choose sub-channels inside this range to avoid interference. Yes. So that is the main reason why we are performing this procedure, this modulation, to shift the spectrum into frequencies which are suited or otherwise required for our system. Yes. And this is performed in a very simple way. So consider that we have a harmonic signal, and the formula describing this harmonic signal is some amplitude, for example, sine wave, some frequency, and initial phase shift. And the difference of these modulation types mentioned here, amplitude, frequency, phase, is that we actually put our message into one of these parameters, into amplitude, into frequency, into this phase shift. Quadrature modulating actually is amplitude. Well, no, it's still phase. This quadrature is basically phase, yes. And the quadrature amplitude is accordingly amplitude plus phase. Yes, we'll talk more about these advanced modulation types, which are used commonly in today, for example, in Wi-Fi, in LTE, and so on. We use this quadrature amplitude modulation in DSL, many technologies, cable TV, yes, Wi-Fi, and so on. All of them use this quadrature amplitude modulation. We'll talk about why, but initially we'll start with these simple modulation types to understand basics. So here you can see a few pictures. That is how amplitude modulation looks like. So you can clearly see here is the signal with one amplitude for 1 and signal with another amplitude for 0. Here is 1, 1, 0. For frequency modulation, we have different frequency of signal. Here you can see one frequency of signal. Here you can see another frequency of signal, yes? And for the phase modulation, we have different initial phase. So here we start as a plus sinus. Here we start as a minus sinus. And, well, from the school trigonometry formulas, you might remember that sinus of A plus B is actually minus sinus A. So we change the phase by P here, yes? And that's accordingly what makes this modulation type. And for quadrature amplitude modulation, we will have change of P divided by 2. Yes, well, but we'll have 4 different signals. So that would be 0, 1, 2, and 3, for example. Yes, and for each of them, we'll have, for example, for 0, we'll have 0 phase. For 1, we'll have P divided by 2. For 2, we'll have P. And for 3, we'll have 3P divided by 2, for example. Yes, that would be quadrature, QPSK. We'll talk about this modulation a lot more upcoming our next lectures, yes. And also we'll talk a lot more about channels. But before we finish, I'd like to mention a few things about channel, about communication line, that actually in this communication line, that is where errors happen, because there happen multiple effects. First of them is actually your signal is getting weaker, so it's called attenuation. So if you send over a distance, yes, the strength of your signal slowly degrades. There is also a noise, which noise is not that strong by itself, but once your signal has been weakened to some certain point, yes, this becomes comparable with noise, and that is when this noise can actually interfere with your signal and make errors. And this noise is actually the reason why we have happening these errors, for which we need Hamming code to correct them and Interleaver to improve this correction. But again, we'll talk about channels, about noise during our next lecture. Today, we have discussed the entire structure. I hope that it's now clear what we will be talking about over our next tasks. That will be modulation, that will be coding, yes, and a little bit about channel and noise. So, do you have any questions? You had some questions, sorry. So we don't need any specific version of MATLAB. Yes, any version will happen. And about error. What happens when we have an error package? Well, when we have an error package, this is like it's from the name an error, yes. And we receive data which was not sent. So basically, in this particular case, let's see, yes, that we have sent this data, which is written in black. And when the error package happened, what we will receive is actually this data. Yes, you can see that these symbols have been inverted where error packet happened. And this is incorrect data. Yes, and there is no way for receiver to know that this happened if we don't use the codes. The code can help receiver tell that actually there is a problem, yes, or even correct that problem on the go. So, and that is exactly how we see the error. The error is seen by calculating this checksum. Yes, so these control symbols have been calculated from this data originally, yes? Well, actually, maybe I can even show how it's calculated, but it's okay if you don't really understand it exactly into all the details right now. I'll just want to show you an example how this is done for this particular code. So let us take this data, 1, 0, 1, 0. Now I will add 3 zeros instead of this control sum, which I don't know yet, which it will be. Then I have to divide it with some polynomial. Yes. And this is very specific division. Again, it's not like what we have discovered in school. This is Galois field 2, this is XOR operation, and so on and so on. We'll talk about this in particular, but right now what we need to do is to perform this division and find the remainder. So now I can divide. Yes, I subtract this, very similar as we use usual numbers, yes. But instead of subtraction, I use XOR operator here. And 1 plus 1 is 0, 0 plus 0 is 0, 1 plus 1 is 0, 1 plus 0 is 1. Then I take this. So 2 times I couldn't divide, and now I have 4 digits, and I can divide. Yes, divide once more. Again, add together and get remainder. This remainder is then written here. Yes, and that is being sent. Now imagine the situation that actually we were transmitting data and get an error here and receive this data. Of course, the receiver doesn't know about this fact, but what will happen is it will take all this combination like this, 1, 1, 1, and perform division again. So again, I do the same division with a little bit difference. Again, it's okay if you don't really understand how exactly I am dividing. I'm just showing you the idea, how this code understands that there is error. And then I get a reminder, which is 1, 0, 0. So the idea is, if the remainder is 0, there are no errors. Now, the remainder is not 0, and that means that there is an error. More particularly, exactly this reminder cell tells us that there is error here. For example, I can show you one more division here. Yes, 1, 0, 1, 0. 1, 0, 0, 1, for example. Now I have error in this position. And this way I should get another reminder. So I will write this. 1. Here we have 1. And you can see that the reminder is different. So this reminder points out to the error at this position. Yes, based on the reminder, we can tell if there is error and where exactly that error has happened. Obviously, if we have two errors, we'll get some reminder which will point to position of one symbol, and accordingly it will perform an incorrect correction of the errors. So hopefully that will answer how exactly this code can see the error. But again, we are expecting to work on this, as you can see from the previous year, around here, our 8th week. Yes, so we'll have group Hamming code, we'll have cyclic Hamming code. Basically, this is almost the end of the course. So for now, maybe you can watch up Wikipedia as well, or any book I have been recommending. If you have any more questions, or if you need additional help, you can write me email as well. Boy, I cannot see what is here. So hopefully it's now more clear to you. Yes. So thank you for joining today, and that is all for today. Next week we'll have, in addition to 2 lectures, we'll also have a practical exercise. You can use any version of MATLAB or Octave, and we'll basically familiarize a little bit with that, because I don't know if you had this experience of programming in MATLAB, so we'll start assuming that you had little experience, yes, and gradually going over the course will make our task harder and harder. So thank you for joining today. I wish you nice.
Excuse me?
Yes?
We don't have a class this afternoon?
No,
Okay.
That is all for today. And next week we'll have 3 classes, yes?
Okay, thank you.
So thank you, and wish you a nice weekend, and see you next week. Goodbye.
Thank you.
Goodbye.
Have a good week.
Goodbye.